basic functions, graphs of basic functions. We just want to be get comfortable with a handful of. Sometimes it's called a library of functions that we want to be familiar with. Begin with the linear functions. A few examples here. Now you'll see references here to whether it's odd or even, and whether it's increasing or decreasing, or where it's increasing or decreasing. Really haven't covered those topics yet. Those come later in Chapter 2, 2.7, 2.8, so I'm not going to emphasize those. But I just want to emphasize what these graphs look like. So if we've got a non-constant linear function, you can recognize that because the right-hand side is in the form mx plus b. Just compare it with y equals mx plus b, the slope-intercept form of the equation of a straight line. If you pick up the f of x, replace it with a letter y, then it's exactly the same graph. So you look at the right-hand side that defines the function. If there's nothing but x terms and constant terms, then it will be a linear function. And if the x term does not have a zero coefficient, it'll be non-constant, meaning it'll either have a positive slope or a negative slope. It will not go straight across. On the other hand, if m does equal 0, f of x equals just plain old b, or 0x plus b, then a set of points in the plane that all have that particular number as their y coordinate. So this looks like f of x equals 15, 25 that's graphed here. So it goes through 0, 25, and 1, 25, and 2, 25, and every other point in the plane that has 25 as its y coordinate. So we call it a constant function. It belongs to the class of linear functions, and then more generally it belongs to the class of polynomial functions, but real simple, so we just call it a constant function. It's constant, its y coordinate, its function value never changes. So these are a couple of, we really hit the linear topics hard in the early sections of Chapter 2, so I don't think these are ones that you'd have any difficulty at all whatsoever. And honestly, they don't show up that much in 2.6 because their graphs, although useful, aren't terribly interesting, for lack of a better word. Special case, which we will see again, of a linear function, non-constant linear, if the slope is 1, and if the y-intercept is 0, it's f of x equals x. We call this the identity function. It's sometimes called the do-nothing. I'd have gone with the capital N there. The do-nothing function, because it does nothing at all. It takes every real number and just does nothing. F of 0 is 0. F of 1 is 1. F of 2 is 2. F of negative 19 is negative 19. Takes every real number, maps it to itself. Although it does nothing at all, it turns out to be surprisingly useful when we look at inverse functions. Later in the course, I think section 4.1, we'll talk about inverse functions. You can tell that two functions are inverses of each other if you evaluate one function and get an answer, and then take that answer and evaluate the other function, and the net effect of evaluating the two functions one after the other is the do-nothing function. So we'll be able to compare there and actually decide whether or not two functions are inverses of each other to see if their combined effect is the effect of doing nothing at all. So it turns out to be quite an important function, and two functions that are inverses of each other are going to, their graphs, the union of their graphs will be symmetric with respect to this do-nothing function. Okay, here are some that begin to be really, really important in section 2.6 in particular. The squaring function and the square root function. Squaring function is f of x equals x squared. Basically, we want to memorize these graphs. I mean, I know you've seen parabolas before, and maybe parabolas in connection to the graphs of quadratic functions, which we'll see more of in section 3.1. But when we're looking at a graph that might be, might be something like that, the question is going to be, how do we get from here to here? How does the graph get from the original, plain, vanilla, y equals x squared function to this other one that's been transformed 2 or 3 different ways? And the expression, if this is f of x equals x squared, how does the expression that defines the right-hand side get from there to maybe, I don't know, something that looks like f of x equals negative 0.9 times x minus 4 quantity squared plus 3. How do we get from the original y equals x squared to the transformed graph, and what does each of these components actually do? What change takes place in the graph? So we really need to have this mental picture in our heads, okay? When we see something that has an exponent of 2 in it, we think, well, might we have started here in order to get here? So you want to have this picture in your mind, or maybe if you just see this picture, you think, oh, that kind of looks like this. It's just oriented differently in the plane. So for the graph of the squaring function, you tie it to the x and y axes, basically at the origin. 0 squared is 0. 1 squared is 1. 2 squared is 4. Negative 1 squared is 1. Negative 1 times negative 1 is 1. And if you square negative 2, you get 4. Nice symmetry. The graph is symmetric with respect to the y-axis, meaning if you draw the y-axis, the two halves of the graph would coincide with each other if you folded the paper, I guess. You put the graph on along the y-axis. And the points directly across each other from the y-axis are called images of each other. They have the same y-coordinate, then the points themselves are going to be equidistant from the y-axis. So important function, important to know the expression that defines it, as well as the graph. The squaring function, I don't know if the scale, maybe the scale on the y-axis is a little different from that along the x-axis, but it's exactly the same size and shape as half of the graph of the squaring function. I meant to say square root. I don't know if I said square root. Let me say square root. The square root function has a graph that's exactly the same size and shape as half of the squaring function. You just take the graph of the squaring function and, well, erase half of it, and then grab the half that's left and kind of reorient it and set it back down, and it'll lie directly on top of the graph of the square root function. Key points on the graph: 0, 0. The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. Those are generally the ones that I use, and just kind of draw the half parabola going through those 3 points. You can add 9, 3, I suppose, if you want, out there. Some limitations on the domain of the square root function, as we know. Try to take the square root of a negative number, and we get something imaginary, and we don't plot points with imaginary y-coordinates on the rectangular coordinate system as we think about it. And let's see, limits on the range as well. We want it to be a function. We want it to pass the vertical line test. So it's just the top half of a parabola. If we included the bottom half as well, of course, it would fail the vertical line test. So when we say the square root of 4, that doesn't mean plus or minus 2. It means 2. It's just a principle, just a positive square root of that number. Up the exponent 1, and we can consider the cubing function and the cube root function. Now these graphs are, well, they're not identical, but they're exactly the same size and shape. If you use a square viewing window, same distance between numbers on the x-axis as you do with numbers on the y-axis, these two graphs will have exactly the same size and shape. When we get to section 4.1, they will be, we will notice that they are inverses of each other. Key points on the graph of the cubing function: 0 cubed is 0. 0 times 0 times 0 is 0. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. So the point 2, 8 is on the graph. Negative 1 times negative 1 times negative 1. Negative 1. And negative 2 times negative 2 times negative 2. Negative 8. So negative 2, negative 8. Key points if you're sketching a quick graph of the cubing function. Something to notice, it's really tough to tell, it's impossible to tell on the scale that I've pictured them here, but if you were to zoom in at what's going on between negative 1 and 1, the graph of the cubing function is actually, it hugs the x-axis more closely than does the graph of the squaring function. You just really can't tell from the scale, but something I might point out, if you evaluate the squaring function at 1/2, what is 1/2 times 1/2? It's fourth, right? So the point 1/2, 1/4 is on that graph. On the other hand, if you evaluate the cubing function at 1/2, what is half of a half of a half? It's more like, well, 1/2 times 1/2 times 1/2? 1/8. So it's half as far from the x-axis as the corresponding point on the graph of the squaring function. So it, as it's close to 0, as the x is close to 0, y is closer to 0 than it is on the squaring function. So it slows down more towards 0, but then it speeds up more. As you move away, as you get to the right of 1 or to the left of -1, the graph is steeper than the graph of the squaring function is. Has all real numbers in its domain, also all real numbers in its range. So the picture that you want to have in your mind when you think cubing function, up to the right, down to the left. The cube root function, if you want to compare this to the square root function, cube root function doesn't have any limitations on its domain. Certainly we take the cube root of 0 and we get 0. Cube root of 1, because 1 times 1 times 1 equals 1. The cube root of 1 is 1. Because 2 times 2 times 2 is 8. The cube root of 8, the cube root of 8 is 2. But why is it that we can take cube roots of negative numbers and get real numbers as the answer? What number can you multiply by itself and by itself again to get -8? -2. Sure, -2 times -2. +4 times -2 again is -8. So -8, -2 is good. And of course, -1 times -1 times -1 is -1. So the cube root of -1 is -1. All real numbers in its domain, also all real numbers in its range. It takes its sweet time. You have to be patient if you want to go very high on the graph of the cube root function. I guess if you want to go as high as 10, how far to the right do you have to go? If you want it to go as high, 10 is the cube root of what number? 1,000. So you have to go all the way to 1,000 if you want to go as high as 10. So you have to be patient, but eventually it will go as high as you want it to go. Also, if you're going to the left, it will eventually go as low as you want it to go. It's just, it takes its sweet time. All right. So those are a couple of pictures. Just etch those pictures in your mind. What, the cubing function, and I'll hurt myself. Or just look really weird doing it. What, something like that? I don't know. Cube root function. Next on the list of library of functions, the reciprocal function. Now the reciprocal function won't get a lot of play in section 2.6 because it's a little bit on the difficult side to sketch a graph. It just doesn't serve well to provide quick and easy examples of these transformations that we'll look at in 2.6. Turns out to be really important in section 3.5, or is it section 3.6? New textbook, I can never remember. But it's the section that we'll do that has to do with rational functions. Functions where there's a polynomial in the numerator and a polynomial in the denominator of a fraction that defines that. Perhaps the simplest non-trivial example of a rational function, and we'll revisit this when we get to that section, is 1 over x. It's the function that takes a number and gives you the reciprocal of that number. Now, can't do this with 0. 1 divided by 0 is what? It's undefined. So 0 does not have a reciprocal, and 0 is not the reciprocal of any real number. This has every number but 0 in its domain and every number but 0 in its range. No points on the x-axis, no points on the y-axis, but every other number, every other real number has a reciprocal. Every other real number is the reciprocal of a real number. Just some considerations. Reciprocal of 1 is 1. The reciprocal of 2 is 1/2. Reciprocal of 3 is 1/3. The reciprocal of 4 is 1/4. And we notice that the farther to the right that we go, the closer the graph gets to what? it gets really close to the x-axis. In fact, we can make it, although it doesn't actually get to the x-axis, this function doesn't, we can make it as close to the x-axis as we please just by going far enough to the right. If we want it to be 0.1 units or less away from the x-axis, just go 10 or more units to the right, and it'll be that close. To the left, it also gets close to the x-axis. Positive numbers have positive reciprocals. Negative numbers have negative reciprocals. How high does this graph go? It goes about as high as you want it to do, right? If we want it to go as high as 10, just evaluate it at a small positive number, really close, evaluate it at 0.1, right? And it'll go as high as 10. If we want it to go as high as 100, how close to 0 would we have to get for it to have a point with a y-coordinate as high as 100? Well, you could go 1,000th, and then it would go to 1,000. You could go a millionth, and it will go as high as 1,000,000. So it's unbounded. If you draw any little open interval that contains 0, the graph goes infinitely high and infinitely low in that interval, and it makes the vertical line where that happens a special line. But we'll have more to say about that when we get to section 3.5. The absolute value function. Absolute value function will be really important in section 2.6 because it's easy to graph. You plot a key point. If you can find the lowest point, or if it's sometimes it's flipped upside down, you might have to find the highest point of the graph. But if you got the middle point on the graph, and then any one point on either side of this, just think about how this graph goes. The absolute value of 0 is 0. The absolute value of 2 is 2, so 2, 2, and 0, 0. And if we plotted many more points, it might start to look like the identity function. Because you take the absolute value of a non-negative number, and it does nothing with it. It just gives you back that number, right? You just erase the absolute value bars, and you get it. But if you take the absolute value of something negative, what happens? You get the positive, so it's got to change it from being -5, let's say, to +5, and it does that by multiplying by -1, changing the sign. So up here you've got the graph of y equals x. Over here you've got the graph of y equals the function that changes the sign of a number, -x. So 2 pieces to the graph of the absolute value function. So if we can get those 2 pieces going, then we can sketch a pretty decent graph of it pretty quickly. So this will be real handy in examples. All real numbers in its domain, every real number has an absolute value, but only non-negative numbers can be the absolute value of a real number, so no negative numbers in its range, no points below the x-axis. And is that all of the ones in the library? Yes, it is. That's all the ones we want to mention right now. So those pictures, the squaring function, square root function, cubing, cube root, reciprocal when we get there, but definitely absolute value right away. You want to have those pictures etched in your mind. So if we have a graph that kind of looks like one of them, we can think, we could maybe get there if we started with a basic function and did one of these 10, the way I count them, 10 transformations that we'll see in this section. So let's go ahead and get started with the vertical shifts, vertical translations. Basically, we'll take the graph of a function and shift it directly upward or directly downward a certain number of units. We want to see what happens to the graph when we do that, and what happens to the expression on the right-hand side that defines the function when we do a vertical shift. So a little bit of experimentation. Let's get the calculator fired up, and then we'll try to explain why it happens algebraically, but first maybe the pictures. For the vertical shifts or translations, we want to begin with the squaring function in the standard viewing window. So let's start with the graph of y equals x squared. Y equals x squared, I want to do a zoom 6. I think the standard viewing window gives us a pretty good look at it. Zoom 6, zoom 6, and we see this. Now I want to compare this, see what happens when we sketch the graph of x squared plus 3 on the same axes. So also x squared plus 3. Any predictions as to what will happen? Does it go up 3 units? 3 units up? graph. And it certainly does. Certainly does. Up 3 units. And if you think about this, f of x is the y value. The function value is the y value. So we had the original, f of x equals x squared, and then we compare to this other one. All the y values are 3 more than they were originally. So we would expect the graph to be 3 units higher. If we evaluate this at a particular number, maybe 2, on the first graph, the y-coordinate is 4. But if we look at the corresponding point on the other graph, the y-coordinate is 7. So every point just gets 3 added to its y-coordinate, goes 3 units up. Y equals, all right, let's redraw the x squared, and then have the calculator graph f of x equals x squared minus 3 instead. So we'll see the original and then see what this one looks like. And I think it's pretty clear what we might think would happen. Is that what you thought would happen? 3 units down. F of x equals x squared minus 3. Hopefully it would make sense that y-coordinates of points on this graph would be 3 units less than y-coordinates of corresponding points on the original. So if we evaluate this one at 2, then the original went through the point 2, 4. On the new one, it's going to go through the point 2, 1. So if we were sketching this without a calculator and someone handed us the graph of y equals x squared, we could look at a collection of points and then graph the corresponding points, leave the x-coordinates alone, subtract 3 from the y-coordinate of every point that we have, plot those points, connect the dots with something that has the same size and shape as the original in the new location, and we'd see that it's 3 units lower than the original. So probably put that, paste that there. And we kind of filled in those blanks, I guess. But there's at least a portion of it there. So when 3 was subtracted to the function, maybe subtracted from the function, or from the expression defining the function, the graph shifted 3 units downward. That's what happened. The other one, of course, was upward. So what I want to do is kind of keep track of each of these new transformations as we encounter them. So I need to remember that it's going to be on page 7. That should be easy enough to remember. So can someone please give me a number from 2 to 9?
6.
I heard 6. I think I'll go with the 6. So I'll go with 6. I heard a 5 over here, maybe, but I think I heard the 6 first, just a fraction of a second, small fraction of a second. Proper fraction of a second before that. Transformation number 1, the vertical, and maybe scoot it over in case I want to label these over just a little bit. If I have the graph of y equals f of x, it could be y equals x squared, it could be y equals x cubed, it could be y equals the square root of x, it could be y equals the absolute value of x, it could be y equals some ridiculous expression that's not special and we've never dreamed of before. But if we have y equals f of x, and we transform it by adding 6, I almost forgot what the number was, adding 6 to the right-hand side, we want to indicate what happens to the graph. Well, what happens to the graph is you shift y equals f of x 6 units upward. It's a vertical shift 6 units upward. Does not change the size or the shape of the graph, just goes 6 units up. 2. Y equals f of x. Suppose you have the graph of y equals f of x. You take the right-hand side of take the expression that's used to define that function and subtract 6 from it. That's going to subtract 6 from every y-coordinate, from the y-coordinate of every point on the graph. And as a result, it will shift the graph 6 units downward. Okay, so the first 2, easiest 2, arguably, of the 10 transformations that we look at, the vertical translations. So I'll come back to this page 7, and I'll continue to update this, probably fill out the page with the 10 transformations that we'll be looking at. So quick examples here. Write an equation for the function obtained. Basically, whose graph is obtained by taking the graph of y equals the square root of x and shifting it 2 units up. So if we, oh goodness, Alt. If we have y equals the absolute value of x, and we want to shift it 2 units upward, what we want is y equals, well, add 2, right? Add 2 to the right-hand side, and we get y equals the absolute value of x plus 2. That's it. We draw the picture if we wanted to, but we don't. There'll be plenty of pictures to draw later. Write an equation for the function f of x equals x squared. Well, we begin with y equals x squared, and we want to shift 3 units down. We take the right-hand side, and we do what? We subtract 3. Just like that. And that will shift the graph 3 units down. We did that a moment ago and looked at the picture. Let's look at the horizontal sideways shifts. These also will not distort the size or the shape of the graph. They just move it sideways to the right or maybe to the left. With these horizontal shifts or translations, if you want to call them that, they're less intuitive as to which direction a given change in the right-hand side will send you than the vertical shifts. In fact, one of my colleagues, Miss Urban, who's now working on her PhD at the, well, somewhere. It's public. Yes, that's where it is. Anyway, maybe it's more public than I thought. Information's out there. She's having a great time, I'm sure. But what she would tell students is, X always lies. X always lies. We'll look at horizontal shifts left and right, and a little bit later, hopefully this morning, certainly Tuesday morning, if we don't get to it this morning, horizontal shrinkings and stretchings of the graph, where we stretch it horizontally or shrink it horizontally. That's also going to be a bit counterintuitive. And if it involves the x coordinate, adding to it, subtracting from it, or multiplying it, or dividing by some number, it's going to have the opposite effect of what you would think is going to happen. So we consider the graph of f of x equals x squared. And then we want to compare that to the graph of x, open parenthesis, x minus 3, close the parentheses, then square it. We want to think of this not as subtracting 3 on the inside or from x or from wherever. Don't even use the word subtract or subtraction or subtracting. You don't want to say that in context of a horizontal shift or translation. You want to think of it as a substitution. You're substituting x minus 3 for x wherever there's an x. And the right-hand side, it might not be one of these basic graphs. It might have x's littered all across the thing. And everywhere there's an x on the right-hand side, you pick that up and put an x minus 3 in its place. An x minus 3 here, an x minus 3 there, an x minus 3 there. Substitute x minus 3 for x wherever you see an x. What happens? There's y equals x squared. It shifts it to the right. Yes.
Well, if you think about factoring, and then you get to that point, wouldn't it be the 0? Like,
yeah.
X minus 3 equals 0, so x would equal 3.
That's, hey, I seldom think about that in that context, but that's really good way to look at it. In that specific case, because we have an obvious x-intercept there, for the factor theorem, if 3 is a 0, x minus 3 is a factor, and vice versa. I like to think of it like this. Suppose we're thinking about the number 0 that's in the range. We know the lowest point on the graph, the original graph, is 0, 0. That's how low the squaring function goes. If we're moving it sideways, the point with the y coordinate of 0 is still going to be the lowest point on the graph. So the question is, if we wanted to shift it 3 units to the right, let's just say that's the goal. Take the graph, shift it 3 units to the right. What we want to do is input x equals 3, because 3 is going to be the x coordinate of that point. So input x equals 3, and then do something to it, and then square, and get 0 as the answer. I'm thinking if 3 is the input, between inputting the 3, the x coordinate of that point, and squaring it, we're going to need to subtract 3 from that 3 to get us down to 0, so that when we square it, we'll just get 0 as the answer. That's another way maybe of looking at it. But certainly, 3 is the 0 of x minus 3 quantity squared. Negative 3 would be the 0 of x plus 3 quantity squared. So if we were to graph x plus 3 quantity squared, whereas the plus might think, okay, looks like we're adding 3 to the x's, so we would think it's going to the right, when actually redraws the x squared and then shifts the graph 3 units to the left. 3 units to the left. Now the way I like to think of it basically is this. We're looking at f of x equals x plus 3 quantity squared. In my crazy way of looking at things, I like to think, okay, x, I'm going to compare this graph to y equals x squared. X can get by with being 3 units less. Less means to the left. X can get by with being 3 units less on the graph of y equals x plus 3 quantity squared, because we're going to add 3 to it before we square. Okay? The plus 3 just kind of gives x extra comfort level or margin or whatever. X can get by with being 3 units less on this graph over here, because we're going to add 3 before we square, and then it'll give us the same y coordinate. On the other hand, for x minus 3 quantity squared, x has to be 3 units greater. On that graph, 3 units to the right, 3 units greater than it does on the graph of y equals x squared, because we're going to subtract 3 before we square. If we want the same y coordinate, x has to be 3 units greater. Well, that's just the way I look at it. It's counterintuitive. You could just memorize the fact that x always lies. So it lies in this particular case. You see the x plus 3 quantity squared, you think 3 to the left. You see x minus 3 quantity squared, you think 3 to the right, and that'll get you there. All right, so let's copy this and paste it somewhere. Oops, it was already there. What do I need to copy and paste? This, I guess. And this one is the graph of y equals x plus 3 quantity squared. Can get by with being 3 units less, because we're going to add 3 before we square. So to the right, to the left. So page 7, where's page 7? There it is. So if we have y equals f of x, and we substitute, don't think subtract, think substitute, x minus 6 for x, wherever we see an x, we will shift the graph of y equals f of x 6 units to the right. On the other hand, if we have y equals f of x, and don't think add, think substitute, x plus 6 for x, wherever we see an x, we will shift y equals f of x 6 units to the left. X can get by with being 6 units or 6 units less on this graph, because we're going to add 6 before we evaluate the function. All right. Special cases, examples. Write an equation for the function whose graph has been obtained by taking y equals the absolute value of x y equals the absolute value of x, and shifting it 2 units to the right. If you want the graph that looks just like the absolute value function, but 2 units to the right of the absolute value function, what we're going to do with the right-hand side.
Absolute value of x minus 2. Wait, to the right?
To the right, we would substitute x minus 2 for x to make it go to the right. So I'm thinking, just like that, yes. Absolute value of the quantity x minus 2. Big difference between that and that. What is the difference between those two? This is to right. This is to down. Being inside the absolute value bars versus being outside. Inside the absolute value bars, it affects the x coordinate because it happens before the function is actually evaluated, before you take the absolute value. But if it's outside, you take the absolute value first, and then it really just affects the y coordinate. Shifts it 2 units down. Write an equation for the function whose graph is, well, it's basically the graph of the cubing function. Looks just like the graph of the cubing function. It's just 5 units to the left of where the cubing function was. So if we begin with y equals x cubed, and then we shift 5 units to the left, you want to think substitution somehow. So what's getting
plus
cubed?
5 quantity, or quantity cubed.
Is x plus 5 getting cubed here? 5 to the left? I think so. I think x plus 5 is getting cubed here. So this one, get by with being 5 units less, so the graph is 5 units to the left. If you substitute, just think about this. If you substitute, and let's graph this because it's our kind of first look at the cubing function. X cubed there, and x plus 5 quantity cubed. I squared it, didn't I? Darn, got to redo it. Yeah, those don't look anything alike. Y equals, raise it to the 3rd power. Okay, so the cubing function, we got that. And then scoot to the left, and we have that. All right, 5 units to the left. Now consider a couple of key points on the graph. If we look at this, where can I paste it? Key points on the graph. The original one, we could consider the point, well, let's go all the way up there just because it's easy. Well, no, that's too high. Right there. 2, 8. 2 times 2 times 2 equals 8. Now there's a point on the graph of x plus 5 quantity cubed that has the same y coordinate because we're shifting sideways. The y coordinates, no change. What is the x coordinate of that point? Well, kind of. Would you say -3? Yeah, -3. Now, -3, 5 units less than 2. But it can get by with being 5 units less than 2 because we've got to add 5 before we cube. So, x coordinates on x plus 5 quantity cubed, 5 units less than the corresponding, by corresponding, the ones with the same y coordinate, corresponding points on the graph of x cubed. So x always lies, it does, yes. All right. Let's see, more transformations. I don't know if we have to do every single one of those, except we're looking at it from a different direction, maybe a different angle. May give us some perspective on this. Rather than saying, okay, here's what's been done to the graph, what does the expression look like? How about, here's the expression, what's this going to do to the graph? So if we start with f of x equals the square root of x, and we add 2. Add 2 to the right-hand side. It's outside the radical, not up underneath the radical. It's going to take the graph and go 2 units. Up, down, right, or left? Up. 2 up. And h of x equals the square root of x minus 1. Again, it's outside, out from underneath the radical sign. So 1 unit down. If we begin with the squaring function and we substitute x plus 1 for x, 1 unit, up, down, right, or left? To the left. If we do the opposite of that, substituting x minus 1 for x, that's got to be 1 unit to the right. Okay, so in each case, we were going back to the original one there to get where we're going. Oh, we got pictures. We've got pictures. So, without cheating, using the graphic calculator, just to try to get an idea, there are 2 transformations going on. Now, a little bit later, when we introduce some reflections and vertical and horizontal shrinkings and stretchings, the order in which some subcollection of these 10 transformations is performed on a graph can affect the final answer. If you're just shifting up and down, right and left, and you've got 2 transformations, doesn't matter whether you go up first and then to the right, or if you go to the right first and then up. You'll get to the same place. So we don't have to think so hard about this. Let's just see what are the 2 transformations and see if we can sketch the graph. Maybe we just figure out where the vertex goes. The vertex is the middle point on the graph of the parabola, the lowest point on y equals x squared. So if it starts here, it's going to end up, what's the x plus 3 do? 3 to the left. And yeah, if we go like to there, where's left? Which way is left? Left is this way. It goes there and then 5 units down. So looks like the vertex goes to the point -3, -5. 3 to the left, 5 down. And then if you can think of some other points, take the point 1, 1 and shift it 3 to the left and 5 down. Take the point 2, 4 and shift it 3 to the left and 5 down. Take -1, 1 and shift it 3 to the left and 5 down. And take -2, 4 and shift it 3 to the left and 5 down. Connect the dots with something that kind of looks like the parabola, y equals x squared. Like that. And then you've got it. It's easier with the absolute value function. I almost wish I'd used the absolute value function for this because you just plot a point and you do that. It's easier. You don't have to worry about the curvature of the graph. Start at the origin and go where with the x minus 2? Where does that take us? To the right. So it's going to go here. And then the plus 1? Up 1. So that'll be the lowest point. 2 to the right and 1 up for every single point on the original graph. So 1, 1 goes there, -1, 1 goes there, 2, 4, maybe there, and -2, 4, probably gonna go right there. So that would be the resulting graph. And then the last one, a little bit more of the same. What's that going to go? X plus 1 is going to send us to the left, and then 2 down. So the vertex, you can fill in the rest of it, but 1 to the left, and then 2 down for the vertex of that graph. All right, good. Oh, and here's a graph, and we need the equation, the expression on the right-hand side defining the function. So let's write the equation that would have this as the graph. Now, sometimes it's tough to tell. Once we start distorting the size and shape of the graph, it'll be virtually impossible to tell exactly the factor by which we did that. But in this case, we're just going to assume that it's a rigid translation, shifting from the y equals x squared, looks like either to the right and then down, or down and to the right. So we could start with y equals x squared, and it looks like this vertex, the print is small, but I think the coordinates are 2, -4. So tough to tell if I'm looking up there. Maybe I can make out the -4. I don't know. But 2, -4 is what I'm seeing here. So to go 2 to the right, so go shift 2 units to the right. It's going to be y equals what?
X minus squared minus 3.
Substitute x minus 2 for x. And that will add 2, strangely enough, to every single x coordinate that points on that graph. And then you're there, you've been shifted 2 units to the right, and now you want to go 4 units down, -4. So y equals x minus 2 quantity squared, and then -4 gets you there.